with this, it is my pleasure to introduce Professor Laura Lechuga, who is who graduated and got her PhD from the Universidad de Complutense de Madrid, and she is now a full professor at the Spanish National Research Council. And her specialty, as many of you might actually already know, is nanobio interactions, nanobio sensors. She has published a large amount of papers in that regard. She has obtained significant awards and recognitions for her work. The list is very long, so I will definitely not spend the time on going through all this list, because I believe that actually this time is the time for our speaker. So I would like to ask you to join me in welcoming our next speaker, Professor Laura Lechuga, who will talk to us about novel developments and recent achievements in nanobio sensors. Thank you very much.
Okay, that's my presentation. Yes. So good afternoon. Well, in Spain, this is the siesta time, so I hope that you can enjoy my plenary and also to have some siesta time. Okay, so well, first off, I would like to thank to the organizing committee, especially to Jorge, to invite me to be here. It's always a pleasure to have a reason to come here to Tenerife, one of the most beautiful places in our country. And also today, I think now with the plenary, we're moving to this shining light on biomedical applications. So everything today is going to be more about how we develop nanophotonics biosensor and how we can apply for clinical diagnostic. Coming from the Catalan Institute of Nanoscience and Nanotechnology, ICN2 in Barcelona. So why we want to develop this technology? Because probably one of the main, what I like to start my presentation is giving a motivation why we want to develop this nanophotonic biosensor. It's not only for publishing, but it's also because, we have identified a problem that we have today in our clinical settings. So, of course, we have in our clinical laboratories, in the hospital and so on, we have excellent laboratory techniques. They are excellent, so we cannot have any problem if you don't feel well. You go to your family doctor, you go to the hospital, you are going to get all kinds of tests, even imagine any resonance, a tomography, whatever. But the problem is that all these techniques are time-consuming. They normally require a very high sample volume, trained personnel, expensive instrumentation. So this is one bottleneck that we suffer during the pandemic. Because if you remember, during the past pandemic of COVID-19, what happened was the following. One, we knew the sequence of the virus. Of course, then it was very easy to identify who was infected or not, just getting a PCR. PCR is a very standard genomic analysis that takes 2-3 hours in a lab with a specialized technician. In the peak of the pandemic, when thousands of people, they really need to get this PCR analysis, what we observed was very long lines of people trying to get the analysis, the PCR. And then there was a delay in the analysis, almost 1 week. A technique that takes 2 hours, people was waiting more than 1 week just to get the analysis. And for example, we know now in Europe that more than 1 million cancer cases were not diagnostic on time due to the collapse in our hospital, in our system. So means people was not able to go even to see the medical doctor to get any single testing. So mean that unfortunately, all these millions of people has died as a consequence of this model of centralized diagnostic. You remember also 1 year later, in March 2021, then we were inundated, the market, with this COVID-19 test. This is a biosensor. And then it was the moment that the pandemic was controlled, and then we stopped the spread of the pandemic. And also, we were realizing that moment, everybody, that the advantage to have an in-home rapid test. So, of course, we have some of these rapid tests for diabetes, for pregnancy tests, and so on. But it was in the moment of the pandemic that everybody, we were just doing, all of us, this antigen test or this serological test at home. So probably the only positive lessons of the COVID-19 is that finally we are able to demonstrate that we really need to have more, better, and faster growth in this point-of-care testing. And I want to share with you one data that is astonishing for me, that if more than almost half of the human population doesn't have access to any single diagnostic, even to the most basic diagnostic. This is a huge number. 45% of the world population is amazing due to this centralized model that we have in diagnostic. So, of course, we have to do something, and we have to solve this problem. And then we have to make testing available to anyone who needs it. So the solution is the following, is to just to go for a centralized model to this decentralized clinical diagnostic. And the idea is that we can use just a single drop. Oh, let's see if I can make it. The technology is okay. Okay. Imagine that we can use just a single drop of blood, urine, saliva, whatever, and you can deploy in a very small device, and then you can get an instant diagnostic just by the bedside, even at home. So this is what we call a point-of-care testing device. So the key capability is that we can have this real-time, label-free, with a very high sensitivity and also with a high level of reliability. And this technology is the biosensor, is the only one, the only technology able to provide these point-of-care devices containing all the functionality of a complete analytical laboratory in one single chip. Just to remember what is a biosensor, this is a very basic definition, but I always like to explain what is a biosensor, because biosensor is a device where we have a physical transducer just in contact with a biological receptor layer, in such a way that this biological receptor layer is completely selective to the molecule that you want to detect in a very complex sample. So when there is this biological receptor layer, just recognize the analyte or the target that you want to detect. Imagine, for example, in a drop of blood, then there is a physicochemical change at the interface that can be directly read by the transducer. So biosensor can detect any substance with a very high sensitivity, with a very high level of selectivity, in a very fast way, and also in real time. Remember that biosensor, the name, is not because it's a sensor detecting biological molecule. It's because biosensor has a biological receptor incorporating with a physical transducer. So the name biosensor came because you are joining two different words, bio with physics, all together in the same device. Okay, so of course there is many biosensors that perhaps some of you are using. The most famous biosensor in the world is the glucose biosensor. 500 million of people use the glucose biosensor every day in the world. And this is a biosensor based in the use of the enzyme glucose oxidase that is completely selective in the catalysis and in the decomposition process of the glucose in our body. And there is also the first wearable biosensor, is also glucose one. Probably you have seen people wearing this white biosensor. This is a biosensor, wearable one, that has some microneedles going inside the epidermis into the interstitial fluid. And there is the biosensor interacting with the glucose in the interstitial fluid. Well, there are many other examples, pregnancy tests, COVID-19 tests, many others. They are very basic biosensor. So as you see, this technology is really a very spectacular technology. And of course, we are just mainly focusing on these clinical applications. And this is probably one of the main applications in the biosensing area. After the pandemic, we have observed that the global biosensor market, for example, in 2021, go more to 25 billion, with an annual growth rate more than 78 billion expected by 2030. But of course, the technology can also be used in the environmental control, can be also used in the ocean control. We can use also in this animal and the health management, or also to control the food, the farming control, everything related with human health, you can see. But also biosensors are being used, starting to be used in the space missions. Because now, one of the main problems in this space mission is how to control the health of the astronaut, but also the health of the cabin, because they are prone to get many infections. So this is a way why also with biosensor incorporating in the cabin, in the astronaut and so on, they can monitor how is the progress of the health of the astronaut. And unfortunately also, because we are living in these times, also biosensors are being used for warfighter, especially for the soldiers to maintain to know what is the health, but also being incorporated in drones also just to make any control of the chemical and biological warfare. In the case of biosensors, of course, there are many different technologies. Probably the electrochemical biosensors are the most used one, just because the glucose biosensor is an electrochemical one. In fact, they are using amperometric detection. But since a few years, there is also a new technology coming that is a very, very competitive one that using paper. This is microfluidic paper-based biosensor invented in Harvard University by Professor Whitesides. And the idea was how to make the very low-cost biosensor technology. And then he has this idea, why not to use cellulose? Because paper is probably the most low-cost technology that you can use. And they are embedded nanoparticles with functionalized with a specific receptor, for example, antibodies, and they have proved how it's possible to make a very low-cost test, for example, for HIV test, in just using some drops during of the patient, costing only 3 cents of a dollar. There is also many other biosensors using nanoparticles, all kinds of 2D nanomaterials, and of course we have all the biosensors using this lateral flow immunoassays, using mainly gold nanoparticles and antibodies. That these are the biosensor when you are using a pregnancy test or you are using a COVID-19 test. But in our case, we decided to use light and to use photonics and optics. And why? Because, I mean, when you are using photonics, we think that is the most competitive technology when you want to develop a point-of-care biosensor device. So I'm going to try to convince you that the light is the most powerful technology. But remember, so what we want to do is to include our sensor chips based on nanophotonics inside the point-of-care device. Let's see if I can make something bigger, and then you can see how. So the idea is that we can incorporate the sensor chips in a point-of-care platform. And remember, making a point-of-care platform is not only to making the sensor, it's not only to allocating the bioreceptor. If we are using optical sensor, we need also to think that we have to include the lasers or LED. We have to include also the photodetectors. Oh, this is working when it's very far away, the computer. We have also to allocate microfluidics and also the photodetectors, electronics, Wi-Fi, wireless connection, and so on. So you can see these are some of the devices that using in my lab. Well, it's not working all time. Okay, using in my lab where we include all these sensor chips based on nanophotonics. Why using photonics? I mean, well, the main reason is because when you're using photonics, optics, or light, they are completely immune to any electromagnetic interference. You can get also a very high level of ultra sensitivity. I will show you later on how we can get even sensitivities of detecting only one single bacteria in the patient sample with this technology. And also because then we can have a label-free. Label-free means we don't need to label our biomolecules. We don't need to make any amplification. I mean, this is one single step. And also we can have this real-time analysis. And of course, then we can get a quantitative information. It's not only to say you are infected or not, because we want to know the number of virus or number of bacteria that are infecting you in any moment. The working principle using on those photonic biosensors is the evanescent wave principle. And the evanescent wave principle is we are monitoring the refracted index change taking place on the sensor surface. So you probably know when the light is traveling in a waveguide media, for example, an optical fiber, the light is not completely confined in the interior. If we just develop the Maxwell equations and then we see how is the propagation of the light is following a model of the electromagnetic field and that we call guided modes. And this guided mode, they have always a part that you can see here, or also here in the video, that extend out of the sensor surface. This electromagnetic field stands out like between 100 and 900 nanometer, depends on the wavelength that you're using and the material you are employing for making your waveguide, but it gives us a very good opportunity to make a biosensor. How? So what we do is the following. We just include inside the evanescent field in this nanometer space our biological receptor, and when there is a biomolecular interaction, so our biological receptor recognizes the complementary analyte, there is a local refracted index change in the surface at the nanometer scale, and then we can monitor these binding events means a change in the refracted index, and then this change in the refracted index means that we can change any optical parameter of the light that is transmitted along our sensor. So at the end, what we monitor is any change of the light, for example, change in the intensity, in the phase, in the polarization, in the momentum, whatever. But we know how to correlate this change in the intensity or whatever in the optical parameter with the number of targets that have been recognized on the sensor surface. So this is the only principle allowing real-time detection, label-free, no amplification. We are speaking about one single step in the assay using this amazing technology. Okay, so this is what we can record when we are looking at the interaction, always real-time, and also label-free. Okay, so in my group, we have developed two main technologies using this concept of the evanescent wave sensing. So the first one is using surface plasmon resonance. Surface plasmon resonance, you can excitate just using very thin layer of gold, normally between 40 50 nanometers. And then we can excitate in the with visible light this plasmon wave that is an evanescent wave component. And then from here, we can just functionalize these gold chips and then to make a biosensor. Of course, as I say, it's not only to make the sensor chip with the bioreceptor, we make also the microfluidics, we have to do all the electronics, and so on. And with this technology, at this moment, we have two-channel biosensor, and we can go for a limit of detection of 10 minus 6 refracted index unit. So this is the limit of detection that we can get with this technology. But because with this technology we're not able to get a very high level of multiplexing, we decided to move to nanoplasmonic and then to localize the SPR and not using thin film of gold, but using metal nanostructure. But we didn't want to use nanoparticles. What we are doing is making nanostructuring of the gold because it's a more reproducible way to make a biosensor. So in my group, we have developed mainly technology using colloidal lithography to make gold nanodiscs, and also to make, we are taking advantage, we just bought Blu-ray, from the market, and we realized that the Blu-ray, they have already a nano-grating configuration, so we just can clean just the upper layer of the Blu-ray, we can deposit gold, and then we have one of the most amazing localized SPR biosensor using these nano-gratings. Of course, we make also all the microfluidics, and recently we have been able to develop everything on a disposable cartridge, where we have the sensor, we have also the microfluidics, and also in a multiplex with 4 to 8 channels that we can also use at the same time. Again, with this technology, well, you can see nice photos here with some of the sensor, and with this technology, we can go for a limit of detection also of the minus 6 refracted index units. Besides the plasmonic technology, my group developed also another technology that is called, based on silicon photonics. This is something invented in my lab, and that we develop a silicon photonics using interferometric biosensor. This is making the silicon level, and this is how we make also all this sensor. And you can see from here that for the nanoplasmonic, the limit of detection we can get is between nanomolar, picomolar. But in the case of the silicon photonics, this unique technology invented in my lab, we can go to picomolar, femtomolar. Remember that this is label-free and no amplification, and directly in the pattern sample, so we can get this level of sensitivity. Everything is done in our lab, the complete in-house design, fabrication, assembly, and also how we develop the platform. Just to go a little more about how working these silicon chips, what we're doing is the following. A light beam is traveling in the sensor, you can see here, And then this is functionalized, for example, with antibody to detect this virus. And then when the virus is recognized, then there is a change in the intensity of the light. And from here is that the sensor is not only giving you a yes or no, you are infected or not, but also we can quantify. I mean, we can also provide the viral load. And this is the most important parameter that they need in a clinical setting. It's not only yes or no. I mean, the most important is to know the concentration. It's like in the case of the diabetic or the glucose. Everybody has a glucose. But they make a difference if you are diabetic or not. It's the amount of glucose that you have in your blood. Okay, so this technology is, as I say, embedded in my lab. It's an interferometric technology where we are using silicon nitride waveguide, and what we're doing here is controlling two modes of the light. So we're just starting with a very nanometric waveguide of 150 nanometer, where only the fundamental mode of the light is transmitted. And then suddenly we make a step junction here, we grow to 340 nanometer, and in that moment we also excitate the first mode of the light. So from here we have a device where two modes of the light are traveling at the same time, fundamental and first mode, and they make an interference. So we make an interferometric device using two modes of the light. And also what we're doing is making a biosensor using the magnetic field. So this is really an amazing device because, I mean, we have operating in the visible range, and then we have with these nanometer dimensions. So we are using waveguide of 3 microns width, and the height is only 1 to 3 nanometers. So this is the only way to control the transmission with these two modes of the light. And we have a very robust and reproducible technology in our clean room facilities. So we fabricate at the wafer level. Each chip has more than 20 sensors per chip. And the limit of detection that we can get with this device is close to 10⁻⁸ refractive index unit. So we can monitor a minimum change of 10⁻⁸ in the refractive index unit. By the way, I have all the sensors here, so if anyone wants to say all the sensors and all the cartridge and everything, and the point of care I have here, I can show you later on, after my presentation. Okay, so this is one of the most sensitive magnetic wave sensor presented in the literature with a very high multiplexing capabilities and operating in the visible range. This is how we're making all the engineering. I'm not going to go in detail, I don't have time, but this is how we fabricate all the sensor chip in our clean room facilities. We make all the polymer microfluidics, normally using PDMS or methacrylate. Of course, we're going to speak about the surface functionalization, but also we make all the cartridge development. We know also how to do all the packaging and storage of the complete biosensor. And of course, we have to work also on the optical subsystem, in coupling, upcoupling, and all the electronics, and so on to make a complete device. And this is our idea. So we're making this possible biochip, this possible cartridge, because the idea, remember, in the clinical setting, you cannot reuse, you cannot mix sample from patients, so I mean that you can use the device only once and then you have to throw away. So that's the reason what we develop our complete point of care, where you just insert your cartridge, do your measurements, and then you can just go for the next one. So the next step is that I want to discuss is the biofunctionalization. So when you have your sensor chip and you think, okay, this is a very complex technology. Well, in my opinion, this is not. The most difficult step is this. When you have to incorporate the biological receptor, and you have to incorporate all these biological receptors by chemistry. And why is it so difficult? Well, because, we have to introduce functional groups in the sensor surface, and then we have to attach the bioreceptor by covalent bonding. But then these biological receptors are alive, so you have to maintain the integrity, you have to maintain the functional of these biomolecules. For example, you are using antibodies. Antibodies only recognize the antigen just by a sequence of 20 amino acids here in the FAP region. So we have to make orientation. And also it's important to control the density. Many people think, oh, I'm going to allocate many receptors, and then I'm going to get a very high signal. This is completely wrong. Because when you have many receptors together, then the target cannot enter due to a steric hindrance. So you have also to calculate what is the optimal density, and you have to allocate a space between the different bioreceptors. And to make it even more complex, finally, you have to test in real sample. You have to use blood, serum, you have to use urine, even saliva, a tear, and we try to do directly in this very complex sample, so you have many non-specific interactions. So we have to know how to develop what we call anti-fouling surface, just repelling all the molecules that you don't want to detect. And then this is in a very complex sample. So making the surface biofinalization is one of the most difficult steps when you want to develop a biosensor on any kind of these devices. Okay, so we're making all kinds of chemistry. How do we control the density, the orientation for proteins, for DNA? Just to show some examples, for example, different strategies, using covalent strategy, using protein G that you can orientate. And also, we have been using some calicin strategy. We're making all this of the direct orientation of the antibodies. But again, when we're trying to do that, there is not a universal protocol. So mean that for each different application, you have to optimize all the parameters. So you have so many parameters, the surface chemistry, the pH, the ionic concentration, the ionic strength, the concentration, and also when you to evaluate real sample, we have to modify the composition of the medium with surfactant, with additive. We have to modify the surface behavior using, for example, hydrophilic polymer, like polyethylene glycol. So I always say that this step is like making a good cocktail. So you know all the ingredients, but depending how you mix, then you have a very good cocktail or not. So this is the same for this surface biofinalization. Remember, we want to do at the end that our biosensor is operating in one step, level-free, real-time, and also to try to get directly in the human sample. Okay, just a few examples how we make for deal with these anti-fouling strategies. For example, if we want to avoid the serum non-specific absorption, we were immobilizing with a calicin technology the antibodies, the protein, and then we try to use different polymers in order to block all the non-specific interaction. So we make with different polymers and also with different buffer, and then you can see here that we have a combination here. We can avoid almost all the non-specific interaction, but also at the same time, the interaction between the antibody and the complementary molecule was also hindered. And then finally, we just move to this position where with using polyethylene glycol, PLL, and also combination with PBST, then we can avoid 94% of the non-specific interaction. So we were able to use the biosensor directly in the serum of the patient. Okay, so with this, my group, we have developed many different applications in many different areas. So mainly, we are going in the area of point-of-care diagnostic, mainly with infection, with cancer, with many other, we make also epigenetic studies and environmental control and so on. So I just pick up a few examples that you can see the benefits of our technology. Just starting with the diagnosis of infection diseases, probably you are aware that now we are just in what we call the silence pandemic, and the silence pandemic is due to the antimicrobial resistant infections. So probably you have here that is one of the major concerns. The bacteria has mutated in such a way that they are completely resistant to almost any antibiotic that we have in our clinics. And unfortunately, the pharmaceutical companies decided to stop doing new antibiotics many years ago. So we don't have new antibiotics, and the bacteria are fully resistant to most, probably all of our antibiotics. So when you go now to the hospital, the situation is the following. If I can show. Okay. So the people just go, and then they make the test, and all the bacteria are completely resistant. And the prediction that we have is that for the year 2050, the number of deaths due to this antimicrobial resistance is going to surpass the number of deaths due to cancer. So in 2050, every 3 seconds, a person will die due to this antimicrobial resistant infection. So we have a very huge problem with this case of the antimicrobial resistance. And also what is the main problem is that when you go to the hospital with an infection, they take your blood, they send to a central laboratory, and they are waiting days and days for the result. So we have identified that the problem is that even sometimes, and even if you're in a good hospital, perhaps in 3-4 days, they say, which is the pathogen infecting you, and second, they are going to give you what is the antimicrobial resistant profile. So we wanted just to try to solve it with biosensor. So we want just to stop, to try to provide a solution that from days we can go give a diagnostic in less than 1 hour. So we have been working on a project where we want to offer our technology for the following. So first we are using a first biosensor when we take the sample. In half an hour, we identify which is the bacteria infecting the patient. Once we know the bacteria, we have a second biosensor where we make a very rapid antimicrobial susceptibility test. So we know which is the resistant profile of the bacteria. And then we have another third biosensor, and now we know which is the best antibiotic for this patient. We are starting to give the antibiotic to the patient, and then we have a third biosensor where we are following this antimicrobial therapy to the patient in order to adjust the concentration in any moment in the intensive care unit. So just to show some of the results that we are able to detect, for example, any kind of bacteria. You can see here how we detect E. coli bacteria directly in the ascitic fluid of cirrhotic patients, and we can detect the bacteria until a limit of detection of 4 bacteria per milliliter. We can detect, many other bacteria, Pseudomonas aeruginosa, Chlamydia pneumoniae, and also with our technology, in less than 25 minutes, a sample of only 150 to 150 microliter, we can detect the presence of this bacteria. In some of these cases, we have a sensitivity close to 1 bacteria per milliliter. So we are able to detect just in the moment a person starts an infection. We also have developed all the biosensor once we know which is the bacteria infecting you, so we can also make the diagnostic of what is the antimicrobial resistant profile. So for example, in the case of the Staphylococcus aureus, this is one of the most prevalent bacteria infecting us, we can differentiate very easily between the resistant one and the non-resistant one, because the resistant one has a specific protein, PB2A, in the envelope, and then we can detect this with a biosensor in a very fast way. And also with our technology, we can detect also all the genes encoding all these antimicrobial production of the enzyme destroying the antibiotics. And then we have also demonstrating how with our technology we can take 2 of the genes encoding this resistance without that we don't need to make any PCR amplification, and we can detect the presence of these genes encoding the resistance with a limit of detection to only 5.8 attomolar with this amazing technology, with a time to result to 30 minutes. So just as a summary, so we can make a very fast direct identification first of the bacteria. Second, we can detect the antimicrobial resistant profile with the problem, and also we have developed all the biosensor for the therapeutic drug monitoring of the antibiotic given to the patient in the intensive care unit. In all the 3 cases, the time to result is less than 30 minutes. So this is really an impressive technology where we are trying now to commercialize and then that we use in our hospital. Well, we have developed also other technologies for infection detection. For example, this is a nice example how we can make a point-of-care biosensor for tuberculosis detection in urine. So you know that the tuberculosis is very difficult to detect, especially people with active tuberculosis. And there is only one biomarker that has been approved by the World Health Organization, that is a lipopolysaccharide that we can find in the urine of the patients. So we just developed a biosensor with a monoclonal antibody, non-commercial one, and we developed in the frame of an European project a complete point-of-care biosensor where we have not only the microchip, where we have 6, let's see if I can put like that. And then you can see we have 6 biosensors in parallel. You see the size of the chip. And also we include here where we have all the optics SLD, all the photodetector, we have all the microcontroller, everything is in the device. We have the cartridge where we introduce, and then we were testing 20 samples from Tanzania. See, look at the sample, all of them are different. You see that they are different density, different colors. And we just draw all these samples directly in the biosensor without cleaning, without filtering. And you can see the real signal from our device where we can differentiate just in 10 minutes who is a healthy person and who is suffering, who is having active tuberculosis. By the way, the sample when arriving to my lab, we don't know, because they are completely anonymized, so we don't know which is positive or not. And only after we got all the result, then they disclose the result, to compare with our technology. So this is amazing that we can detect sensitivity, specificity close to 100%, no pre-treatment, so just directly all this sample, 150 microliter, and in less than 10 minutes. And recently, we have also developed a multiplex plasmonic biosensor for virus, respiratory virus, where we can just making all this cartridge with plasmonic, you can see here. And then in this cartridge, we can immobilize a different bioreceptor for the main infecting respiratory virus, like anti-influenza B, respiratory Cilian virus, and the SARS-CoV-2. And also with one sample from the patients, so we can detect with a very good sensitivity. We can differentiate without any problem the negative from the positive, but also we can also stratify the patient according to the different virus that is infecting the patients. So we have this ability to discriminate one single test, the four respiratory virus, 20 minutes with a very high sensitivity and selectivity. Okay, of course, we have been working also with SARS-CoV-2, as everybody, so we developed also a biosensor. The main difference is we were detecting the complete virus, the SARS-CoV-2, the complete particle virus, and we were able not only to say if a person was infected or not, but also to detect in the viral load between 100 to 10 to 7 virus per milliliter. Of course, the pandemic was over when we finished the biosensor, but what we decided is why not to use the same biosensor, because we spent a lot of time developing all this SARS-CoV-2 biosensor, and now we are using to make the surveillance of the evolution of this coronavirus in all the pets and animals in Europe. So we are working with a big consortium trying to monitor how is the evolution of this coronavirus, mainly in cats, hamsters, and dogs. And then we have developed 2 different biosensors, and we are monitoring also the surveillance, something that is very important in order to avoid the outbreak of a new pandemic due to coronavirus. Okay, if I have time, the second example I wanted to show is about cancer. As you know, cancer is one of the major global health problems. Even in the antimicrobial resistant infection is going to be even worse. But the problem is that this is very bad news, but 1 in 5 people will develop cancer during our lifetime. So the numbers are really increasing every year. And the only way, because we don't know how to stop the cancer, but the only way is to make a very good prevention, to try to make the diagnosis of the cancer at the moment of the onset of the cancer. So, because we need this new diagnostic and also these new therapeutic tools, what we wanted to do was something different. It was not only to detect the classical biomarker from cancer, but also we decided, well, why not to try to go for something more different, that is looking at the epigenetics biomarker. So the epigenetics biomarkers are related with the alteration in the cellular pathway in the onset of cancer. So we decided why not to try to monitor at the same time, what is the change in the DNA methylation, alternative splicing taking place in the nucleus of the cells, the presence of microRNA, DNA mutation, everything together in a multiplex platform, and then we can have a much better diagnosis of the early stage of a cancer. So we have been demonstrated, for example, how with our technology, we can detect microRNA. MicroRNA are very short RNAs of only 20 nucleotides, are implicated in many diseases, like in cancer. The problem, they are circulating, and they are excreted by our cells, and they are circulating in blood, in urine, in saliva. But the problem is that they are very short, they are in a very low concentration, sometimes in the picomolar range, even attomolar. And they're difficult to detect because there are many homologous. I mean, there are very many similar ones. So we developed a biosensor to detect lung cancer in blood plasma using the microRNA 21.5p as a biomarker. This is how we develop all our chemistry, not going on details, and how we make all these anti-fouling strategies. And then with our technology, we have been able to detect the amount of microRNA until a limit of detection of only 381 picomolar. So this is a very low. Remember that there is no amplification. This is one single step reaction. But of course, I mean, one thing is doing this in the lab, but then we need to take we always go to real sample, and then we were able to get real sample, and then, as I said, we got 40 sample. As I said, when they arrived to my lab, we don't know the sample if they are from healthy people, from people with cancer, and then with our biosensor, we didn't have any problem to stratify who was healthy and who was suffering for this lung cancer. And this is one microRNA. We are extending now to more microRNA. We have a very good statistical correlation also with quantitative PCR. So this is, I mean, and we use only some drops of the blood of the person to do the analysis. We have also demonstrated how we can do also with our biosensor the direct detection of the methylation of the DNA. So this is, the methylation means that you have these cytosines, these methyl groups in the CGP regions of the DNA, and this is something that is different when you are getting cancer. There is a complete alteration of this number of cytosines, this number of methyl groups. So it means that the cancer has a unique methyloma. The problem is that you want to detect this double-chain DNA, and then you have to detect the number of these methyl groups. Well, you can do with techniques in molecular biology, but they are very long time. I mean, as I say, in the lab, you need, a lot of procedures and so on. So we just developed a complete new technology where we call the triplex helix approach, where we make a kind of herpes, just a double DNA, that are able just to detect the double DNA directly. So we can just trap the double DNA directly, and then in a second step, what we do is the following. We just first, with our triplet helix approach, we capture the DNA, and in a second step, with a specific antibody, we just quantify the number of methyl groups in the DNA. So you can see the real signal from my lab, where we just trap this double DNA, and now we can see the different signal because have different number of methyl groups. So we are able to quantify. You have 1, 3, 5 methyl group just in the DNA. So it's a demonstration how we can use this for the methylation, looking at the direct methylation in a direct way, the methylation of the DNA in the pattern sample. We are analyzing now this for several genes related to lung cancer, also with clinical samples, and so we want to offer, especially for two types of cancer, lung and ovarian. This is the two cancers that are so difficult to detect in the early stage. They are only detecting when they are in a very late stage, and we want to offer this kind of multiplex detection in our multiplex chip, where we can have all these events at the same time, and then we can detect who is starting this cancer. Just another example that we developed a few years ago that I really like also to tell is how we want to make early detection of the colorectal cancer. As you know, colorectal cancer can be detected only in hospital with a colonoscopy. Colonoscopy is a very aggressive and also very expensive technique in the hospital. But we know also with the clinical knowledge that this is one of the few cancers having an immunological reaction. So when you are having the first cancer cells, they just producing our polyps, they start to emit what we call a tumor-associated antigens. These tumor-associated antigens start to flow in our blood, and as a consequence, our immune system starts to fabricate antibodies to destroy these antigens. So if we monitor the presence of this specific, the presence of these specific autoantibodies, then we can know who is starting a colorectal cancer. It looks like that this process takes place 3 or 4 years before the cancer can be detected in the hospital. For us, this is just a simple blood test. So we already have 4 of these tumor-associated antigens, and we are detecting with our biosensor in a multiplex way, so we can detect all of them, also with a very good limit of detection. It was not so easy to find a real sample in this case, but we were also to evaluate the real sample, and we have proved that we have a biosensor where we make a direct and label-free detection of the presence of these autoantibodies in the blood of the patients with a very good sensitivity. And also we have correlation with the clinical result. So we think that perhaps in the future, this is some of my dream, we could offer a very easy point-of-care test where we can detect who is starting a colorectal cancer and we can avoid colonoscopy. And just to finalize this part of the cancer, of course, I mean, this is what I am showing here is mainly diagnostic, so how we make a very early diagnostic of a cancer process. But we wanted also to know, but can we use also the technology for something more, for the treatment? Well, this is something that we started, really new, a new research line. So we wanted to know if our technology can be a complement, complementary to go for this advanced personalized medicine. How we can do that? So what we wanted to do is to create what we call biomimetic nanoplasmonic sensor, where we emulate just the membrane of the cell, and we decorate with different receptors in order that we can also evaluate different therapies, and also we can also test, for example, which are the best anti-tumor T cells in order to give this immunotherapy to the patients. So until now, we have been also with this technology, for example, also doing the screening and the evaluation of monoclonal antibody that you can use also in the treatment of cancer. And we demonstrate in that case for the antiviral therapy for COVID-19 with very good result. And recently also we make the assessment of the checkpoint inhibitors. This is a way also to avoid the propagation of the growth of the cancer cell as an immunotherapy for cancer. And all our biosensor can be able to detect this in less than 20 minutes. So we really think that our technology could help in identify what is the best immunotherapy for each person in a very personalized way. Just to finish my presentation, I just want to make just a few comments, because we are working also how to use incorporating MOF and molecular organic frameworks, and also incorporate metal organic polyhedra in order to use the biological receptor. It is really complex, all this biological receptor. We decided in collaboration with the group of Daniel Maspok, also in SN2 in my institute, we just joined forces, and we decided why not to use all this MOF and MOP as chemical receptor to be very selective for different pollutants. So we started several years ago, and the first thing that we did was to use just a MOF in order to make a gas sensor. In that case, it was for CO2. But it was several years ago. It takes a long time for us how to incorporate the MOF on top of our sensor surface. Remember that my devices are optical one, working in the visible range. So when you are just incorporating the MOF, sometimes we observe it just an absorption of the light or a scattering. So we really need that the light is traveling in the sensor. So we have to adjust the thickness and the morphology, everything of the MOF in order to have transmission of the light in our devices. And finally, we demonstrated that we have a very good sensor for the CO2 detection, a very selective one using this approach. But then, because using MOF was so complicated, in order to adjust the wavelength and to avoid all the scattering, avoid the absorption of light, we decided to go for another step, and then we decided just to move to use the metal organic polyhedra that the group of Dani Maspok is fabricating in my institute. And these metal organic polyhedra are more at the nanoparticle level, so means that the incorporation in our biosensor can be more easy. And also what we are using are these cuboptohedral MOP, and we are using rhodium 2 MOPs, and also because they fabricate in such a way that they have a very high density of surface functional groups. So we can use some of these functional groups to make the covalent bonding with the surface of my sensor, and then the other can be use in order to be completely selective to the analyte or the molecule that we want to detect. Okay, so this is how we are making, this is how we are integrating in our biosensor. Remember that our biosensor have this height of only 3 nanometers. The width of our waveguide is only 3 microns. So we are now incorporating all this MOB in our biosensor. This is how it looks like in the lab. And we fabricate one in order to be completely selected to benzotriazole. And this is a demonstration how the MOB fabricated by my colleagues are completely selective to benzotriazole. We use as a control TN of 10, and then the biosensor of using real-time signals, so we can get all this, with a very high sensitivity detection of benzotriazole and not TN of 10. So with this, we have demonstrated this is a very good strategy to detect all kinds of micropollutants. We are detecting heavy metal, pesticides, pharmaceuticals. We have been, as I showed before, this benzotriazole. We have also published imidacloprid. Also, we have also tested all this working in tap water in real samples. So we think it's open and the way to a very competitive sensor devices for in situ environmental control. We have only in 15 minutes we can get the signal with a very high sensitivity and a very high accuracy. And just recently we are also moving to do something more on biosensing, more in the biomedical area. There are not unpublished results at this moment. We didn't finish completely, but we think also that we can also immobilize, to include DNA receptor in this MOB. And at this moment, also we make this covalent immobilization. We realize that we need to use a tail of polyadenine in order to give flexibility to this DNA. And then we are just immobilizing. We can use DNA, RNA, whatever, and then we make a hybridization, and then we can recognize complementary strand. We are using now to monitor microRNA related to melanoma cancer cases. And we can demonstrate until now that we can detect and quantify clinical relevant concentration of this microRNA in a very simple way. And also the idea to use this MOB is also because we can make a better control of the density of the receptor that we can allocate in our biosensor. Okay, still, this is a non-finishing work, but still we are getting very good results, and we are very excited because now we are incorporating in our multiplex platform, so we can incorporate different MOB in different channels. So it means that with one single sample, we are able to detect different microRNA of different pesticides, whatever, just using one single sample. Okay, so I want just to finish my presentation. This is a summary of all the application that we have developed in my group. So my group, beside the technology, because all the technology is fabricated or embedded in my lab, and all the technology and all the point-of-care devices, that then we go also for a myriad of different applications that you can see in our publication or on our website. Just to make just a final conclusion, I hope that I demonstrated, I convinced you that the point-of-care photonic sensor for decentralized analysis is one of the most powerful technology, and we need all these biosensors. We need this for the fast, direct, level-free, high sensitivity, low sample volume, a massive diagnostic that we are going to need in this post-pandemic era. Nanophotonic biosensors are one of the most competitive technology. But remember, the surface chemistry is the key. This is the most difficult steps. You can do fancy chips and fancy technology, but the surface chemistry is really difficult, and we have not to be underestimated. And also, we need multiplexing capabilities. We have devices now with 8-channel, 7-channel, even more operating at the same time using one single sample from patents. So in the future, this is my prediction for the future, the diagnostic and the medicine of the future, we can do whatever you want to detect with all this biosensor chip and anytime, any place. So this is, this is going to be the place for the hypochondriac people. You get up in the morning and to say, oh, I'm going to measure today this and this and this, so this is going to be fantastic. Okay, and all the technology that I show here are made in our country. We're starting a new spin-off company. It's going to be my third company, Heroica Diagnostic, in order to commercialize mainly for infections detection. Just to thank my group, as I say, well, we have a multidisciplinary group. We have been working for many years people from physics, engineering, and biochemistry, chemists, all together. So we have to be working together. Sometimes it's difficult, but it's the only way to get all this work done. And of course, I want to thank you and gracias for your attention.
Thank you very much for the excellent presentation and really impressive results. So we have time for 1 or 2 questions from the audience. Yes.
Then you have different in specific interactions you have to deal with.
Yeah,
so in your experience, which is the fluid which is more, let's say, easier to work with?
Easy to work. Well,
in terms of reducing these...
Yes, I mean, well, the main problem is that there is not a standard technique. So when you develop an application, as you say, I mean, you have to go one by one. I mean, you have to start from the very beginning to deal with all the non-specific interactions. The most difficult one for us is blood. Because I mean, because we're working in visible range, so this is also a lot of interference, and that's the reason why we can work with serum and plasma. Now we are trying to do also in blood, but it's the most difficult one. For example, when we were working with this acetic fluid from the cirrhotic patients, it was a very clean fluid, so this was also, I mean, a very good fluid for measuring. We don't have also problem with urine normally, so urine we know how to deal with all these non-specific interactions. But in any case, I mean, any fluid, saliva, for example, is a very dense fluid, so you have to do some little of pre-treatment, so it depends. But also depends, I mean, the pathology that you are looking for, because many of them are in blood, plasma or serum, so you can monitor there. Some of them are in urine. People are using also sweat, but there are very few biomarkers that you can detect there. So, but of course, yes, I mean, we have to deal with all this non-specific. And the bad news is there is not a universal recipe. I mean, you have to do one by one.
Okay, there is one more question from the back.
Yes, as always.
Okay, thank you. It is related also to the surface functionalization. So I have learned the only few things that I know about biosensing is that bacteria and viruses are completely different to deal with. Can you comment a little bit on the surface functionalization differences when you are treating bacteria or viruses?
Yes. Well, the bacteria, the viruses we're detecting. So depending, I mean, what we have to deal is with the medium where we are detecting. For example, we were detecting the virus in saliva or in nasopharyngeal fluid, so we have to do some pre-treatment, of course. I mean, you cannot do directly. In the case of the bacteria that we're detecting in urine, for example, or in serum or plasma, we can detect directly when we have all this antifouling in order to avoid the non-specific interactions with the other components in this complex sample. But we are dealing with bacteria, with virus, I mean, no problem on that. In fact, the SARS-CoV-2, we're detecting the complete virus. Of course, it was deactivated with ultraviolet light before measuring in our labs, but we don't have, I mean, we can detect without any problem.
All right. So in the interest of time, I suggest to postpone any further Q&A, maybe tonight during the welcome reception. We will now thank you very much again.
Okay. If you want to see the devices I have in my bag, because they are so, I mean, this is nanotechnology, so I'm traveling with them. They're really amazing. I will show you now. Thank you.
Thank you.